Okay, Astronomy 10, welcome. So today we're going to be talking about galaxies in general. Last time we talked about our galaxy, the Milky Way. So here's a diagram that shows our little region of space and some of the galaxies that are nearby. So in this diagram, we're right in the center. Milky Way galaxy is right in the center. Up here is a little key. It's showing different types of galaxies. We're going to learn about that in just a little bit. So spiral galaxy, well, that's what we are. We talked about that. In fact, we're a barred spiral. Remember that? Elliptical galaxy, just kind of a big blob, doesn't have quite the beautiful structure like a spiral. We'll talk about that. Then irregular, those are just really a big group of stars, and it's they're kind of in a mess. We're going to talk about that as well. So here you can see, so we're here, and then there are two galaxies that we can actually see with the naked eye if you're in the southern hemisphere. If you're in Australia, South America, South Africa, you can see these. The small and large Magellanic clouds. Magellan, when he was exploring, legend has it that the first couple times they saw that, they're like, hey, there's these clouds in the sky, but they noticed they never went away. The clouds were always there. Of course, they didn't know what it was. Now we know that those are two little galaxies that are actually very close to our galaxies. They are irregular because they're getting torn apart. The gravity of our galaxy, the Milky Way, is so much greater. It's just ripping these things apart. Remember we talked about the Roche limit, right? So as they get close, they're getting ripped apart, right? And so small Magellanic clouds, we can't see them up here. What we can see from up here is Andromeda. Andromeda is a huge galaxy. It's bigger than we are. It's a spiral as well. It also, so Andromeda is several million light years away, and so we're heading right towards each other. There's a gravitational attraction, so we're headed right towards each other. At some time from now, some billions of years from now, we're going to collide or do some sort of get really close to each other, and we'll probably form and become a big galaxy of some sort, of some type. You can see Andromeda has little galaxies that orbit it as well. You can see those with binoculars. This is so cool. And from California, if it's a clear night, you're out in the desert, find Andromeda, right? You find Andromeda, you use your app on your phone and find Andromeda. You can see it in binoculars. It's a big fuzzy thing, and you can see at least one of the galaxies that's orbiting it. It's large enough to see in binoculars. It is cool. So there's Andromeda. Then there's some other little ones, right? There's one here called the Sagittarius dwarf galaxy, right? I'll show you where that one is as far as just the direction. So last time when we talked about our galaxy, the Milky Way galaxy, talked about the center of our galaxy, that if you look towards the constellation Sagittarius, it looks like a teapot. You can see it from Pittsburgh area just fine on a clear night, and it looks like a teapot. And then the center of our galaxy is kind of where the teapot spout is. That's very convenient. So the spout of the teapot, and just a little ways off of that, is the center of our galaxy, where the black hole is, right? I talked about that last time. There's all kinds of stars orbiting the black hole, right? Well, here, the dwarf galaxy is they call it Sagittarius, of course, because it's in the direction of the constellation Sagittarius. It's another dwarf galaxy, sort of beyond, the stars that are in the constellation. Those are stars within our galaxy, but as you leave our galaxy and go out, right? Because our galaxy is a world unto itself. It's this spiral thing. Well, then you have to leave that world and go really far away. Then there's another galaxy here, right? And there's not really much in between. So galaxies are worlds unto themselves, each containing billions of stars, right? There's billions of stars in our galaxy. There's billions of stars in Andromeda galaxy. These smaller ones have less. There's still a lot, hundreds of millions, right? So those are what galaxies are, right? Worlds unto themselves. So, all right, let's just talk a little bit more about black holes. I talked about them before, but we're just going to talk a little bit more because at the center of galaxies, certainly the center of our galaxy, we have a black hole. So let me just talk about black holes just a little bit, just to refresh that. So we'll go down here and we'll go like this in my studios. Where are you, Felix? Well, I'm in the Felix studios, right? There's Universal Studios and there's Felix Studios. Kind of the same thing, right? So let's talk about black holes. So we know what causes a black hole is if you just have enough matter. If there's enough stuff that gravity is collapsing it, it's going to collapse into a point. Remember, if you have our sun at the end of its life, it's going to turn into a white dwarf, right? And the electrons, there's enough force, it's going to keep it from collapsing any farther. If you have more stuff, it'll collapse through the electrons and you'll have a neutron star. Well, now you have the density of a neutron, which is very, very dense. So it'll collapse to a neutron star, and then that will hold it, and the neutrons themselves are so dense it can't go beyond. But if you have even more stuff, certainly a star that's, say, 25 times the mass of our star, certainly something that big, well, then you'll have enough mass that it will crunch through that, and it'll crunch down to what's called a black hole. And it's called a black hole because even light itself can't escape. Remember, if you had a cannonball and you shot it from Earth, right? If it had enough velocity, it would eventually escape Earth's velocity. That's called escape velocity. Well, the fastest that anything can move is the speed of light. So what happens is a black hole, it has so much gravity, the force of gravity is so great that nothing can escape, because even photons that would be trying to get out, they don't have enough velocity to escape. So they would not. They would be turned around. So even light itself does not go fast enough. So there's so much. The force of gravity is so strong that nothing can escape, because nothing can attain the escape velocity and then we call that region, right? So you would go far away from the center, right, where you just have infinite mass, and then right at the point where light could escape, right? So if there was a photon here, well, it would be able to get out. We call this the event horizon. You may have heard that term in sci-fi. It's called the event horizon. So this is the parts of a black hole we care about. There's the center itself, and then there's the event horizon, right? So nothing could escape, right? So if you in your spaceship with your buddy Zork from Alpha Centauri and you're cruising around, and he's got a souped up spaceship, he goes, hey, let's go by the black hole, right? You're like, oh my God, don't do that, right? But he could go, if he's going fast enough, right, he could do something like that. And like, yeah, you could do that, right? Could he do something like this? No, nothing. And even if you're going the speed of light, which a spaceship can do, but nothing can escape a black hole once it's there, right? What's also perfectly fine is you could go, and spiral in, that's perfectly fine, right? You can do that. But what you can't do is escape. Nothing can escape a black hole, right? Okay, and that other part is called the event horizon. So that's just kind of a review of black holes, right? These are my notes. Okay. Let's go back here. Oh, I know. We're going to do, let's talk about types of galaxies. So I talked about that a little bit. I said up here that we were a spiral galaxy. There's elliptical galaxies, irregular galaxies. Let's talk about that. So we'll go back to my. You folks are lucky. You get to see my artistry in action, right? Because everyone knows I'm a good artist, right? So that's why people take my class, because I draw so well. Okay. So we are a really pretty spiral galaxy, right? We have there's a central bulge. Now when I say we, that's the Milky Way galaxy. We're what's called a barred spiral. So we have our central bulge actually has what they call two bars coming out of it, And then, you know, and then coming out of here, you have the spiral arms, right? And then there's more spiral arms, and it's a really pretty thing. Our sun is out in the suburbs, and we're on a spur, right? So meaning that our spiral arm doesn't actually connect to the central bulge. A lot of the spiral arms do, and we're out here in the suburbs somewhere, right? So we're out here in the suburbs someplace, you know. And then, so this is called, it's a spiral galaxy. Then if it has these bars, it's called a barred spiral galaxy, right? Then an elliptical galaxy is either circular or egg-shaped or an oval shape. And it's just a big, it doesn't have the structure that a spiral does. And what it has, and this is just full of stars, billions, even trillions. These can be huge. They say that they can form when two spiral galaxies collide and eventually form. They will lose their structure. And in the center, it can be more dense, so you'll have the nucleus in the center where it's more dense. And these stars aren't just hanging out. They're orbiting, right? These stars are orbiting. So you're going, that looks dangerous. Well, yeah, space is pretty dangerous, right? Everything's dangerous, right? So that would be an elliptical galaxy. So it's just kind of a big grouping is what it just looks like a big mass of stars with, you know, billions and hundreds of billions, even a trillion stars in these things. These are quite large, right? It's just that. Then there's another star, there's a galaxy, excuse me, there's another type of galaxy, it's called irregular. It's just a mess. And I said that these were what the Magellan clouds were, the ones that we can see. If you're down in Australia, you can see them with the naked eye. They're just a mess. They may have had some form, but now they're near our galaxy, right, our Milky Way, and they've lost their shape because the gravity is pulling it, and they're orbiting, and they're getting pulled into our galaxy. So they're a mess. They're just all torn up. And these are a lot of small galaxies that are near bigger galaxies. They look this way. They're called irregular. They're just a sloppy looking thing, right? Then there's one other kind called peculiar. Peculiar have a certain shape, but there's a peculiarness. Like say if two spiral galaxies were coming in close contact and the gravity was interacting, where you might have some kind of thing where you have, you know, the nuclei, if, like this would have been one galaxy, this would have been another, but instead of the spiral arms looking pretty, they're all kind of maybe deformed this way because they're going by each other, right? And these may swing by and then come by again because of gravity, and they'll just, so we'll see them in the various stages, right? So these have a structure, but it's a very peculiar structure, and it depends what's happened to it, like what caused it. Did it run into another galaxy? There's all, man, I encourage you, go to NASA, just type in galaxies. There's galaxies where you'll have a huge galaxy, but the nucleus, so the galaxy is all spinning in one direction, and the nucleus is spinning in the other direction. It's crazy. So they believe that what that was is you have one small galaxy kind of, or you have two galaxies collided, but one galaxy was spinning one way, the other way, and the nucleus in this one survived, so it's spinning this way, and of course right here where you have all this friction, where one is spinning one way, it's really bright, because you have all kinds of star formation, right? Starbursts are happening there, because all the gas and molecules all rubbing, right? And then we learned about disks, how stars form. Well, you have a lot of activity like that, so this just bright with, you know, blue stars. There's a lot of supernova because the blue stars, remember, they don't last very long, so when they die, then they explode, right? So I encourage you to go to the NASA website and just look up galaxies. There's so many, but for our purposes, we're just introducing this. We're talking about four main types: spiral galaxies, right? We talked about the structure last time. Elliptical, irregular, and then peculiar, right? So we're just going to talk about those types of galaxies, okay? So let's go back up here to this screen. So we talked about this. All right, we talked about black holes, we talked about types of galaxies. So let's go on, see what else I want to talk about here, and then we're going to talk about something very important called Hubble's law. So here's just some examples of beautiful. Oh, this is a really good picture. In fact, one of the movies I have posted, right? It's an image taken from the Hubble spacecraft where there's nothing but galaxies. That is a must. Go and look at that. They have the 3D animation, right? It's just spectacular. It's the most important image ever taken, right? Because it shows the structure of the world that we live in, right? And it just repeats. Everything in this picture is a galaxy. So here's a galaxy, here's a galaxy, here's a galaxy. This is taken, of course, from Earth. Or it's taken from the Hubble Space Telescope, which is orbiting Earth. It's only 300 miles up there, right? So it's orbiting Earth, and it took this picture, and it took it. So all of these objects are outside of our galaxy. Galaxies. So these are worlds unto themselves, each one containing billions of stars. So billions of stars, billions of stars, billions of stars, and incredible distances between these, right? Millions of light years in between these galaxies, and it just continues and continues. We see this. Then these, of course, form structures. We've talked about that before. Or you'll have local groups. That's the picture I just showed you before. Our local area. Then galaxies will form clusters, where there's a cluster of groups. Then you'll have superclusters. Well, you'll have clusters of clusters, and they form these huge thread-like filaments in space. It's like bubbles, and those are the hugest, the biggest structures known in the universe, right? And it's all formed by galaxies and gravity interacting. It's amazing, right? And it just repeats. So this is nature. This is nature at the largest scales that we're able to witness it, right? So, and there's color too. We talked about redshifted, right? Most galaxies are moving away from us because the universe is expanding. We're going to talk about that next week. Some galaxies, like the Andromeda, are headed right towards it. On the local level, there's still things coming at us. So Andromeda is blue shifted. It's coming towards us. Most galaxies are moving away though, so they're redshifted. Okay. So let me go through these. There's just a lot of. I encourage you to go to NASA website, look at galaxies. Right. Here's a beautiful one. I think. Is that the Sombrero Galaxy? I'm not sure. But here you can see gas and dust along the edge. It has a beautiful nucleus at the center. And just more examples. All right, look at the videos. It has a good it has a good simulation of what two galaxies merging would look like. Let me go through here. Okay, so we saw that, and let's talk about Hubble's law. Okay, Edwin Hubble in the 20s. He was an astronomer down in Southern California, and he was examining, studying galaxies. And there was a time when they thought those galaxies, those wispy spiral things, that they were just structures within our galaxy. They thought that was the universe. He realized that those things were beyond our universe, or beyond our galaxy, right? We have our galaxy, and there's galaxies beyond that, worlds unto themselves. But what he showed, so distance. Remember, we talked about a parsec. A parsec is about 3.2 light years. Well, megaparsec, so millions of parsecs. So this is really far. These are millions. One parsec is 3.2 light years, so there's millions of them. So big distances. We need this when we're talking about galaxies, because light years is now too small, right? The same way inches to San Francisco doesn't make sense. Light years doesn't make any sense when we're talking about galaxies. They're too far away, so we need to talk about mega, right? Millions of galaxies. And here's velocity. So this is how far. So we live here on Earth. So here's our galaxy. We're measuring galaxies. We're measuring galaxies that are far away. What he found is that the farther galaxies were, so the distance. So the farther a galaxy was from us, the faster they're moving away from us. You're going, what? That seems weird. So galaxies that are close to us. Well, the ones that are really close, they could be moving towards us, right? But as you get farther away, so galaxies that are farther, they're going away even faster. If you go look at even farther galaxies, they're going away even more faster. So that's not some fancy space thing, right? There are fancy space things. This is just kind of, Raisin Bread does the same thing. And you're like, Raisin Bread, why are you talking about Raisin Bread? Well, because I'm going to show you. When I was a kid, I would help my grandma make bread, right? And my grandfather would always be in the tool shed. I'd help him, then I'd help my grandma. She baked her own bread right back in those days. So, and what you do is I never liked raisin bread. She didn't make raisin bread. My other grandma did, but I never helped my other grandma make bread though. But so what you do is you make the bread, and then there's yeast in it. You put it. You leave it to rise, so the dough has to rise. So she'd put like a little, they call it a cheesecloth over it. Then the dough would rise because the yeast is multiplying, right? The dough would rise. Then once it rose, then you put it in the oven. But let's just take look at a couple of raisins, right? So we'll look at these two raisins and these two raisins. So these two raisins, I don't have a ruler here, but this is maybe 3/4 of an inch, right? If I was to measure that. And the distance between these two raisins is maybe 2 inches, right? So you put the dough down, it rises, right? Well, now look, these two raisins that are close together, so they went from 3/4, now maybe that's 1 inch. So this length has only increased by 1/4 of an inch. But this length went from 2 inches to maybe 3 3/4 inches, maybe not quite 4 inches. So what happened is this raisin that was far away, at the same period of time that this one only moved 1/4 inch, this one here moved maybe a full inch or 1.5 inches. So because it was farther away, it moved farther away as things were expanding. So things that are already far away move away at a faster rate, right? Because during the time that this expanded, well, this would have had a velocity to go from here, where here it had to have more velocity because it traveled a greater distance in the same amount of time, right? So the universe is the same. Our universe is expanding, right? That's something that Edwin Hubble discovered. And so galaxies that were already far away, as the universe expands, they continue to move away farther or faster and faster, just like raisins that are already farther will move away at a faster rate than those that are close, right? So now there are spacey things we're going to talk about, but that's basically Hubble's law, right? Think about the raisin bread. It's a good way to remember it. Let me go back to this diagram here. Yeah, so Hubble's law. This is definitely going to be on a test, right? You want to know that Hubble's law, so that galaxies, the farther away they are, the greater their distance, the faster they're moving away from us. That is Hubble's law, right? That's very important. What that means is that, so we can look at the redshift. Remember we talked about redshift. Go look at my video on spectra. If you look at spectra 2, the second one on spectra, I talk about the Doppler effect, right? So you can measure the redshift. So you see, we can measure the redshift of these galaxies here. They're greatly redshifted, and they have a very great redshift. Well, you can measure their speed, right? And now here, using Hubble's law, here's the thing. If you can measure the redshift, when you know the redshift, you know the distance. So, because you can measure the velocity, the speed, based on the redshift, and when you know the redshift, you can get a pretty good idea of the distance. So it was an amazing discovery. In fact, Hubble, Einstein, and a Jesuit priest all got together. At the time, they thought that the universe was static. In fact, Einstein even changed his famous equations to show that the universe was static. But Hubble and this priest, who was really good at physics and math, they convinced Einstein that the universe, they showed him the data and showed him that the universe was indeed expanding. So then Einstein decided, okay, the universe is expanding. And then after that, everyone was kind of like, okay, the universe is expanding, right? And then Einstein changed his equation to show that what the empirical data, right? Scientists, when you present them with data, you change your ideas. You don't do what people do on the internet or on cable news TV where they keep their ideas and they discard data, right? Scientists don't do that. Scientists, you look at the data and you change your idea, right? So that's the way that works, okay? So we talked about black holes, we talked about types of galaxies, we talked about Hubble's law, right? Hubble's law is going to be on the test. It's like raisin bread, right? Make sure that you know about that. let's talk about one more thing. We're going to talk about dark matter. So I'm going to make one more drawing here. I got a little bit of space. There'll be enough space here. There'll be enough space. So remember we talked about dark matter. Dark matter, so the stars that are in our galaxy. So we have our galaxy, right? I'm just going to draw this small because I want to show more. So we have our galaxy. Well, the stars that are on the outside of our galaxy, way out here, far away from the center, they're going too fast. They're going way too fast, right? They should be. They're going so fast that based on the gravity that's inward of them, based on the mass that's inward of them, they should be flung out into space, but they're not, right? And all galaxies do this. As we look at other galaxies in space, they do that too. So what they're saying is that the only thing, one of the ways you can explain it is if there is more matter than we can account for. If there's a lot of matter that's outside of the galaxy that we can see. So what they're saying is that there must be sort of, remember there was a halo around the galaxy? Well, there's another larger halo of this, and it's called dark because you can't see in the dark. So it's called dark matter. That's what the name came from, right? So they say so what happens is galaxies, we can see this much mass, but we measure this much mass, right? If we look at the effects of gravity and how galaxies interact and how they act themselves, they need this much stuff in order to behave the way that they do, but we can't see that. Nobody has a jar of dark matter. However, we can measure it. We can see its effects by measuring things. So that's one of the basic foundations of this thing called dark matter. Galaxies have way more gravity than they should. And it seems that the gravity is spread out over a much bigger area than the galaxy itself. Remember, our galaxy, it's maybe 80 to 100,000 light years. But the dark matter halo, right? The galaxy itself may be 10 times that, right? It might be 10 times that. So perhaps 1,000,000 light years across, for if you include the dark matter, right? So that was dark matter, right? So you want to know that. Make sure you watch the other videos that I'm posting, right? Make sure that you watch that. So let's go back to Hubble's law, and that's dark matter. Okay, so we talked about dark matter, Hubble's law, and the rays of it. Let me just do a quick perusal. I think we got it covered. Let me just check my notes quickly, and you're fine. Oh yeah, and then you want to make sure you watch the video on quasars. What I did is I was going to do a separate video on quasars, but I found this one on the internet. I go, this guy's saying just what I wanted to say, and now he's not quite as debonair and dashing as I am, but bear with him, right? Give him a break. But it's a good video. The graphics are a little better. You're going to miss my artistry, right? The graphics isn't as good as my great artistry, but it's a good. But you want to know about quasars. And then I'm going to post two files in Canvas where I give you hints on some of the test questions and what you want to look for about quasars in that video. But it's pretty self-explanatory along with what I've written. So you want to make sure you understand quasars. There's going to be several questions on quasars on a test. So you want to be sure to read my comments and look at that video. And okay, folks, so everyone be safe, and we'll see you next time. Bye-bye.